Now that we've taken a look at truth tables, we can now do some proofs using truth tables. And what do I mean proofs? Well, suppose I have two formulas P and Q, and I want to know if they're logically equivalent to each other. Well, they're logically equivalent if the truth conditions of P are the same as the truth conditions of Q, which means that if we have some formula P and some formula Q, if the truth table column outputs exactly the same values in the exact same order, then P is logically equivalent to Q, which means that whenever we have P in our formula, we can just substitute it with Q and it's the exact same thing. So let's just jump straight into an example and see how this is done. So I have a question, and I want to know if P and Q is logically equivalent to not P or Q. So first we build our truth table for P and Q. For all of our propositions, we need to build a truth table for that. Then we piece together, one connective at a time, everything that we need in order to get both statements. So for instance, for P and Q, we have to put P and Q together. But for not P or Q, first we have to put P or Q together, which is shown in the fourth column, and then we can add the negation to it in the fifth column and then find more truth values. So let's do the truth tables for all of these. So first, P and Q. When is P and Q true? Well, P and Q is true only when P is true and Q is true. So it's going to be true in the first row, and it's going to be false in all of the rest. So the truth conditions for P and Q, we could say is 1, 0, 0, 0. Now, for P and Q to be logically equivalent to not P or Q, then this would also have to be 1, 0, 0, 0. So let's see if that's the case. Well, P or Q. What's the truth conditions for P or Q? Well, P or Q is true when at least one of P or Q is true. So it's going to be true in the first 3 rows because P is true in the first 2 rows and Q is true in the 3rd row, but it's going to be false in the 4th row because P and Q are both false. Now, not P or Q, we just take the negation of the previous column. So 1, 1, 1, 0 is going to become 0, 0, 0, and 1. And of course, I'm just taking the negation of the previous column. So, are P and Q and not P or Q logically equivalent? Well, the answer is no. And why is it no? It is not equivalent because the truth conditions for P and Q and the truth conditions for not P or Q are not identical. Therefore, these are not logically equivalent. Let's do another example. Let's ask, is not P and Q logically equivalent to not P or not Q? So we just did P and Q before, so first I'm going to do not P and Q. So I have to build P and Q before I can build not P and Q. So P and Q, we just did this. This is going to be 1, 0, 0, 0. Now if we take the negation of that, the values just flip. So not P and Q is going to be 0, 1, 1, 1. Okay. So we have the truth conditions for not P and Q. Now we have to do not P or not Q. But in order to do not P or not Q, first we need to do not P, then we need to do not Q, and then we can put them together with or. So not P, this is just the opposite values of P. So if P is 1, 1, 0, 0, then not P is going to be 0, 0, 1, 1. And again, just to connect these visually, this P column changing to not P, we just reverse the values. Similarly, with the Q and not Q column, we just reverse the values again. So instead of 1, 0, 1, 0, it's going to be 0, 1, 0, 1. Okay, so now that we have not P, not Q, we can do not P or not Q. So not P or not Q is going to be true when at least one of those is true. So in the first row, not P is false, not Q is false, therefore not P or not Q will be false. In the second row, not P is false, but not Q is true, so not P or not Q is true. In row 3, not P is true, therefore not P or not Q is true. And in the fourth row, they're both true, so of course not P or not Q will be true. Now we can take a look at the truth conditions for the two formulas we want to compare. And they are exactly the same. Therefore, yes, they're logically equivalent. Which means if I ever have not P and Q in a proof somewhere, I can substitute that in with not P or not Q because they're exactly the same thing. So that's what logical equivalence can do for us. Now, I have a couple exercises. The first thing I want to do is I want to show that P or not P is always true. And this is known as a tautology when it's always true, meaning that every single value in our truth table is going to be 1. So let's do this. Let's build our truth table. First thing, we have to start with P. And then I'm doing P or not P, so the second thing I have to do is build not P. And then finally, I can put them together to make P or not P. So let's build the truth table for P. Well, P can either be true or false. What does that mean for not P? Well, if P is true, then not P is false. And if P is false, then not P is true. Now, P or not P is true if at least one of them are true. Well, in the first row, P is true, and in the second row, not P is true. Therefore, P or not P is a tautology, meaning that every single output is a 1 here. So P or not P will always be true. And of course, P or not P could be something more elaborate. Like, for instance, it might look like A and B, or not A and B. So this is also P or not P. So if you treat A and B as P, then this is really just P or not P. So in a proof, these P or not P might just not be expressed with just one proposition. It might be a combination. So just like this A and B is similar in both, so we can treat this as P or not P, and this is another important thing to look out for. Finally, I want to show that P and not P is always false, otherwise known as a contradiction. So I can do the same thing as before. Of course, what is the truth table going to look like for P and not P if it's always false? Well, it means that every single thing is going to output a 0. So once again, we can build the truth table really quick. If P is true, then not P is false. If P is false, then not P is true. P and not P is true only when P is true and not P is true. But they both can't be true at the same time. So they are both false. So here, all of the outputs are a 0. Therefore, this is a contradiction. So these are proofs using truth tables. Now this is different from proving using rules of inference, which we're going to get to eventually, and it's also different from using logic laws to reduce statements, which is coming next. So there's essentially 3 ways of proving things, and I'd say the most simple way is to prove using a truth table. So definitely find yourself some practice problems, work on these. If there are any questions, you can always ask. So please do ask if there are questions.